Welcome to 7.5 Enthalpies of Combustion. You need to be looking at page 125 to 126 to help with this video. So our lesson objectives for today are to be able to recall the definition of standard enthalpy of combustion, to know Hess's law and be able to use it to perform simple calculations. For example, calculating enthalpy changes for reactions in enthalpies of combustion. So first of all, our definitions. From the last chapter or the last video, we already know the definition for Hess's law, which is that the enthalpy change is independent of the route taken. And we also did the enthalpy of formation definition. So today's video is going to look at enthalpy of combustion. And the definition for enthalpy of combustion is the enthalpy change when 1 mole of a substance is completely burned in oxygen at 298 K and 100 kilopascals. So again, I've put this on 3 lines, just like the last video, because this is a 3-mark exam question, and you get 1 mark for saying the first line, which is enthalpy change when 1 mole of a substance, 1 mark for saying completely burned in oxygen, and 1 for saying at 298 K and 100 kilopascals. So that's our definition. We now need to use it in Hess's law. So a quick revision of what Hess's law means. So as we said, Hess's law meant that the enthalpy change is independent of the route taken. So what that means is going from reactant A to product B is going to involve an energy change, and that's going to be the same no matter what route we take. So if we go from A to B, it's going to be a certain energy change. If we go from A to C to B, it's going to be the same overall energy change. So the enthalpy change, delta HAB, is going to be equal to delta HAC plus delta HCB. Now, last lesson we looked at using enthalpies of formation in Hess's law. So today's lesson we're going to use enthalpies of combustion. So here's a typical example of an equation that we might be trying to work out the enthalpy change for the reaction. So we're taking hydrogen and carbon and oxygen and using it to make ethanol. So this is in fact an enthalpy of formation. But we don't know it and we're trying to work it out. So first thing we need to do is, because we're dealing with enthalpies of combustion, we need to have the products of combustion in a box underneath. So when we did enthalpies of formation, it was the elements we had underneath. Now we need to have the products of combustion. And of course, if you look at the elements we've got, we'll just look at the left-hand side. If we look at the elements we've got on the left-hand side, then we've got hydrogen, carbon and oxygen. Now oxygen obviously can't combust because it can't react with itself. If hydrogen combusts, it's going to give water, and if carbon combusts, it's going to give carbon dioxide. Remember, it reacts completely, so we won't get carbon monoxide, we'll get carbon dioxide. So if we draw the products of combustion at the bottom, this is what we get. Remember, the stoichiometry needs to be correct, so because we've got 3 H2 molecules, we need to have 3 H2Os, and because we've got 2 carbons, we need 2 carbon dioxide molecules. So next thing we need to do is draw our arrows in. So with enthalpies of formation, we have the arrows going up because you're going from the elements to the compounds. In this case, the enthalpies of combustion are going to go from the elements or the compounds down to the products of combustion. So the arrows are going to go down. So we can draw those in like this. And you can see the arrows go down. Now, the next slide shows the numbers that we need to put in, because we've got 3 molecules of H2, so the value we need to add in is going to be 3 times the enthalpy of combustion of H2, and we're going to call that delta HC1. And then we need 2 lots of the carbon combusting, because we've got 2 moles of carbon combusting, so we're going to need to have a value of 2 times delta HC2, where C2 is the enthalpy of combustion of carbon. Now, as I said when we talked about it before, oxygen can't combust because it's already oxygen. Oxygen can't react with oxygen. There's no arrow for the oxygen. So our reactants are going down to the box at the bottom, to the combustion products, and our product is going down to the combustion products. And because there's only 1 mole of the ethanol, you only need 1 delta HC3. So if we now apply Hess's law, we can say the enthalpy of our reaction that we're trying to work out is going to be 3 times delta HC1 added to 2 delta HC2, and then take away delta HC3, which we can see here. Now the reason you're going to add the C1 and C2 is because the arrow, you're going with the arrow, so our enthalpy change of combustion is going from H2 and 2C to the water and the carbon dioxide, so the arrow goes from the reactant to the product of combustion. However, when we are going to go from the products of combustion up to the product, you're then going against the arrow, so that one needs to be taken away. So we can also write this as the sum of the enthalpies of combustion of the reactants take away the sum of the enthalpies of combustion of the products, because the enthalpies of combustion of the products are always going to be going against the arrow, and for the reactants it's always going to be going with the arrow. So several things to watch out for. First of all, as before with enthalpies of formation, if there's more than one mole of a reactant or product, you need to take this into account, just like we did on the previous slide. Secondly, the enthalpy of combustion is 0 for products of combustion. So, for example, if you had CO2 or H2O as a reactant or product, then there would be no arrow for that compound. And lastly, you need to be clear whether it's enthalpies of combustion or formation that you're using. It's the values you're given that are important, not the one that you're calculating. The exam board very often asks you, for example, to calculate an enthalpy of formation using the enthalpy of combustion, because they know you'll get confused, or they know some people will get confused, and will use the wrong one. So make sure you're very clear that you're using it's the values that you're using that decide whether the arrows go up or down. Okay, so back to our lesson objectives, which were to be able to record the definition of standard enthalpy of combustion, and to know Hess's law and be able to use it to perform simple calculations. For example, calculating enthalpy changes for reactions from enthalpy of combustion. And as usual, if you don't feel that you've met those lesson objectives, then make sure you either rewatch the video or read the textbook before you come to lesson.